the Tech Insider podcast. I'm your host, Nick Hume, founder of Hume Consulting, where we focus on technology strategy, sustainable digital infrastructure, and technical diligence for capital markets. Tech Insider explores leadership, emerging technologies, and infrastructure trends with executives shaping the future. In this episode, I sit down with Philip Johnston, co-founder of Starcloud, an ambitious startup building AI data centers in space. We discuss the physics of orbital compute, from free solar power to shedding heat directly into the vacuum of space, along with the unique challenges of thermal management and satellite stability. We also unpack the realities of launching hardware aboard Starship, the potential for space-based inference at the edge of Starlink, and whether breakthroughs in terrestrial energy, like SMRs, make orbital compute obsolete or more necessary than ever. Coming to you as part of the 2025 Tech Insider Summer Series, this one's a deep dive into the final frontier of infrastructure. Enjoy. So, Philip, welcome to Tech Insider. It's great to have you on. We met, a few months back, and I got to tour the cool facility that's in your background there, and meet some of the staff you got working with you at Starcloud. Starcloud is this really ambitious kind of opportunity or company that's looking at data centers not here on Earth but in space. So, love to talk to you about this. This is super interesting. Hopefully, this is super interesting for others as well. I don't think I'm alone in that thought. You've been on a lot of different podcasts and in the community talking about things. So there's obviously a lot of interest. Tell us about Starcloud. Tell us about yourself, the origin story, and what inspired you to kind of get going with Starcloud.
Yeah, for sure. Thanks very much for having me on, Nick. So Starcloud, as you mentioned, we're building large data centers in space. Initially, we'll provide cloud services to other satellites, but the ultimate aim is to compete with terrestrial data centers purely on an energy per cost basis. And this is made possible. The longer term vision is made possible by coming launch vehicles, for example, Starship from SpaceX and New Glenn from Blue Origin, which are set to lower the cost of launch very dramatically, potentially 10 to 100x cheaper than we currently have. So, the general thesis came about. I'd spent some time working with the space agencies of various governments, and my co-founder Ezra, who's our CTO, has spent the last decade designing satellites, and our third co-founder Adi was a principal software engineer at SpaceX working on Starlink. And so we had all seen basically that the launch cost is coming down very rapidly. It used to be about $60,000 a kilo 10, 15 years ago. With Falcon 9, the launch vehicle from Starship, it's now $6,000 a kilo. That's what we pay. And it's potentially heading towards a $60 a kilo. So another 100x reduction with Starship. And so there's lots of things that become possible, things like space-based solar, which is a concept, not a new concept, from the 70s, where you have enormous solar panels, and then you somehow beam that power down using microwave or laser technology. So initially, actually, that's what we were looking at, was space-based solar. And then we got thinking, well, almost all new energy projects terrestrially are being built to power data centers. And so it's quite likely that the energy we beam down will also, be used for compute in some form. And so then we were thinking, okay, well, the problem with space-based solar is you have like a 95% efficiency loss getting power from space to Earth, because, it gets eaten up by warming the atmosphere, essentially.
Sure.
So instead of that, what if you had a cheap way to get the data center to space? So that, instead of beaming the power down, using it for processing here, put the data center in space, and then you don't lose 95% of the power through transmission. And so we basically reran all those numbers that we had done for the space-based solar. And we found that the launch cost that we require for space-based solar is on the order of $10 to $20 a kilo to make space-based solar work. The launch cost required to make data centers in space work, in our mind, is around $400 a kilo. So it's much closer to where we are right now. And so okay, well, the first thing we should do and would do if we had low-cost launch would be building large data centers in space, basically. And so that's then the basis of a white paper we put together last year. And on the back of that, then we got started.
Nice. That's very cool. So just going back to, you were thinking about doing the transmission down, was the 95% loss just too big was that the catalyst to then move it the flip way around, like to basically pull the compute up into space? Okay.
Yeah, exactly. If we could have let's say 20% loss, that would make space-based solar within the realm of possibility with a reasonable launch cost, with say a few $100s a kilo launch cost, which is still a lot cheaper than we're currently at. But when it's such a high, when it's such a high loss, then that just means the launch price we need to make this work is just way too far
Yeah.
away from where we currently are.
Yeah.
It's possible that it will work at some point. I'm not saying space-based solar won't work at some point, but I'm just saying that the launch price needed is much lower than the launch price needed for compute in space. And so that's
Yeah.
the first thing you should do is basically that.
The first hurdle, yeah.
Yeah.
That
Yeah.
should be interesting. So like it's on their website, and you can go to starcloud.com and check this stuff out. And you've got an impressive visualization or animation about the size of what this thing could look like up there, and the large solar panels and the containers essentially that are docked across this. What would you call that thing? Like a big. What do you
Huge
refer
solar
to
panel.
this? It's just a huge solar panel. Okay, cool. I
Yeah.
thought I was just miss using the wrong language, but it's an impressive animation and things. And so I think the scale of this thing was something like 5 kilometers in on one of its lengths, right? So it's a huge structure.
Yeah.
Sort of where do you start? So you go, that's the end goal of a supercluster or of large scale. I think the 5 kilometer thing gives you about a 5 gigawatt worth of power pull or utilization. Where do you start? What is something that you're working on today to get to that point? I think we talked last time we spoke. You were doing some testings of GPUs and simulations, etc. You were waiting to do some actual launches as well. So maybe just starting with,
Yeah.
if the video people can see on their website is this enormous, amazing, cool thing in space, break it down from where guys are today, and then just a journey towards that super cool, large 5 gigawatt.
Yeah, for sure. Yeah, definitely encourage people to have a look on the website starcloud.com, and on the front page you'll see this concept video we have. So the steps are basically, in a few months we're launching our demonstrator satellite. That's a much smaller. It's about the size of a small fridge, 60 kilogram small sat. That's going to have about 100 times more powerful GPU compute than has ever been operated in space before, including an H100 from NVIDIA for the first time, an A6000 from NVIDIA, and a few other chips. Yeah, and go on, Nick. What are you going to say? Yeah.
The No, I was going to ask what has been up there. Like, what's the most
Yeah.
performant thing that's been thrown up into the atmosphere?
The most performant is probably a Jetson Orin chip. That's the thing. I mean, we're actually flying with a Jetson Orin even on that satellite, and we're using it for telemetry and flight controls and things like that. Um,
It's like a
which, as I
Raspberry
say,
Pi in comparison now, right? Like, from a
yeah,
performance point of view versus things. Yeah.
yeah, compared to an H100, it's literally 100 times slower. So yeah, that's the current state of the art. And lots of times when people talk about doing data centers in space, they are talking about putting Jetson chips up, which is literally 100 times less performant than what we're going to be doing. So yeah, that's the first one. And the purpose of that mission is really to prove that we can operate data center grade terrestrial chips in space. So as I say, nobody's ever really tried. We've done a whole bunch of ground testing on that. Particularly, we've put H100s in a cyclotron and shot protons at it, and done thermal vacuum, all of these types of tests. So now it's just left to see if all of those tests function in
Real
space as they do.
in
Yeah.
reality, a simulation. Like, when you throw that thing into the simulation, what are you expecting things to fail? Are the things that are failing, or the telemetry you're like seeing, is that what you anticipated? Is it sort of close to reality? Are you seeing things that, oh gosh, that changed, that was different, it was better, perhaps it was worse? Like,
Well,
is there anything you can
when
share
we
there?
Yeah, well, I mean, for example, there's actually no data on lots of this stuff. So, like, nobody's ever put an H100 in a high velocity proton beam before. So it's not really like we have a huge expectation, to be honest. Um, what what it gives us is the the tolerances. So we now have proprietary information on what level of radiation will cause an H100 to fail,
Hmm.
and that's kind of like new knowledge. Like we went into it with a fairly open mind about where that level would be. We're also keeping it quite close to our chest where that level is, because it's not cheap to do a cyclotron test. Um, so yeah, I mean, but what will be interesting will be to see how closely it is matched by what we observe when we actually launch the thing into space. Um, so yeah, I mean, the two big areas that we've been doing development work on are, number one is the thermal management of these things, because they produce a lot of heat in a very small area. And so for the first one, we've got this big immersion cooling system. And number two, because obviously in space it's a vacuum, so you don't have convection or conduction from the air. And number two is the radiation shielding part of that. And also, to some degree, the software that we're writing to adjust for bit flips. So like voting algorithms that some of our team have been writing to make these things work.
Yeah. No, it's interesting. When we met, we were talking about, the heat challenge, right? So you've got the power coming in, you're obviously powering these chips, and in this example, in the smallest case, a single H100, but I mean, it still draws significant amount of power, produces a
Mm.
significant amount of heat. And so, and you talked about like first time type stuff. So back in 21, we were putting those kind of chips in immersion tanks and kind of crossing our
Mm.
fingers because, on A100s, et cetera, over
Yeah.
the time. And so, it's very novel way of doing something, but you don't know until you try. And you kind of got to just throw caution to the wind with some of this stuff with very expensive electronics that, you need a lot of spares on. And so it's, you got to have some stones to start doing that stuff. So then you've got this at H100 going up. It's kind of, maybe what's the total power usage of that system that you're testing with as it relates to, you got 5
Yeah.
gigawatts in your future. What's that going up, in the interim?
Yeah. So peak power draw on that's about 1 kilowatt. It doesn't have a kilowatt of generation, so we have battery storage. And it's really a demonstrator.
Yeah.
So yeah.
Well, and so actually, that's a good question. So, like, when you've got that, you've got essentially like a node up there with, a GPU in there. Is that being air cooled? Is that being liquid cooled? Is that, you talked about immersion? And then I was thinking about, from a networking point of view, is that a single node? How are you then communicating to and from that device, or are you at all? And you talked about batteries. How do batteries? You have to pick a certain type of battery that can kind of coexist in that environment that's nothing off the shelf. And I think my follow-on questions would be, what things do you have to develop yourself and develop your own vertical IP on, versus I can just go buy this off the shelf down at Vetco, down the corner here, or I can go
Mm.
to an electronics store and get the things I need to buy. Is that sort of, tell us
I
how
mean,
that sort of thinking.
that's a good question. I mean, part of our proprietary IP is figuring out the ways we can tweak commercial off-the-shelf parts to make them, because if you can use commercial off the shelf, it is just 100 times
Oh
cheaper
yeah.
than any space grade stuff. So I mean, we've just done an enormous amount of tweaking of like commercial off the shelf parts to, like for example, like with these chips, various different designs of heat sinks, and we're building our own heat sinks, but they're mega cheap compared to anything you would if it was space um, rated from an aerospace company. Um, so yeah, I mean that's like the biggest or a very significant part of IP is figuring out how to use these commercial off-the-shelf parts in a space environment. And that's some of the data that we're hoping to get back is to see where some of these parts fail, and we'll test them to the limit. Once they're in space as well as through the testing that we've done on the ground. But yeah, so I mean, we'll be doing some interesting demos on that one. Like we'll be the first to train a model in space, the first to run high-powered inference in space, first to do fine-tuning in space. And yeah, to answer your questions about is it one node or two, so it's two chips. They're internally networked. But yeah, that's basically the extent of it. Or two of these high-powered GPUs anyway, and then there's other smaller chips.
And then just thinking about the cooling of that, and maybe we can think about the way out or the way in. We can go either way, but I was thinking maybe we'll start on the way out. So from a cooling point of view, a typical data center and on land is getting, is air cooled. Maybe the next generations are all liquid cooled as a default, but this is an air cooled environment with a heat sink and a fan sort of pulling that heat off that node,
Mm.
and having cold aisle containment and all this stuff, and hot aisle containment. How are you dissipating that heat? You talked about radiators when we were together and
Yeah.
developing that yourself, and you're obviously doing heat sinks yourself. So just without sort of spilling too much IP,
Yeah.
high level, how does that work?
Yeah. So, I mean, I'll talk about the first two satellites. The first one, it's like an immersion called what we call phase change material. So, it's essentially immersed in this proprietary mixture of phase change material. And what that means is it's something which is solid, that melts as it warms up, as it goes through the cycle facing the sun, and then as it goes in Earth's eclipse, that solidifies again, and it helps to smooth the thermal load, basically. So that's for the first one. It's quite a rudimentary system, I'd say. The second one is the second satellite's launching in October next year, and that's going to be at least 10 times more power, max power draw, and 100 times the power generation as the first one. So, and the way that we're doing that is these very large, low cost and low mass deployable radiators, and we're designing from scratch those in-house because they don't. It'll be by far the largest
Yes.
commercial radiator in space. The largest radiator is currently on the International Space Station, but they're extremely expensive and heavy. Our radiators need to be much, much lighter and thinner and cheaper than that.
Yes. And then, like raw materials for those things, are they, I won't say hard to come by, but expensive? Are you using, is the cost associated with the alternative, is the raw material the problem? Is it the engineering involved? Is it just there's only one user, so there's no volume? Like,
It
what's
it
the,
it yeah. Without giving away too much of what we're doing, in the old, expensive launch environment, you would do everything you can to optimize mass, and that would mean having extremely expensive, composite materials and all this type of thing. In the new lower cost environment, you're less mass constrained, and that means you can work with cheaper materials that are slightly higher mass. And
I
so
see.
that's the route we're going down.
You
Is
get
like
more opportunity?
how
Yeah, okay. So you have more
how do
options.
we make this thing as dirt cheap as possible? I mean, cost is the if we're going to have a 1 megawatt of, of thermal dissipation radiator, these things are massive. They're like the size of a tennis court at least, and so we can't be using um, very expensive composite materials.
Totally, totally. And so, yeah, so that's sort of scaling up and out. And then, then they're scaling out to the 5 gigawatts and the 5 kilometer, array of solar panels, et cetera. How are there technological advantages or uplift in the solar panel kind of quality or efficiencies? Are there things that you need to see for that to be viable? Are there already today's materials could go up and be utilized in the white paper you discussed?
Yeah.
Is there, because there has
Today's
been improvements in that area. Um, you
yeah
know, I don't know the specifics of is it a 2x every 3 years or whatever, but uh, are you able to use
no,
those
it's
things
nowhere
today?
near. Yeah, no, it's we're pretty close to the limit that we can. We're certainly like, you know, it can't get more than 50% more efficient than it currently is. Like that, like there's the physical limit of that. We just wouldn't allow it. So until very recently, people were using for the exact same reason. People were using very expensive cells, what they call gallium arsenide. It's a way that you can draw energy from different wavelengths of light. And so what that means is it's slightly more. It's it's more. You can draw more power per unit mass, but it's about 100 times more expensive than using terrestrial silicon. And when I say more power, I mean like 30 or 40% more power, not like 10x more power. So in a world where launch cost is low, what you do is you just use the cheapest terrestrial silicon cells you can, and you just put more of them up there. And
Yep.
that's exactly the approach that Starlink's used. I think they're publicly on record as using these terrestrial silicon cells manufactured in Taiwan. So that's the approach that we'll be using as well.
Yeah, well, I guess to your point, if your mass is no longer a problem or is becoming less of one,
Mm.
you've got plenty of space, no pun intended, to deal with. Like you're not constricted or constrained by uh, size, right? So other than
Yeah.
literally getting it up there, so the lower cost makes sense. How? Let's say you've got that thing up there. We might have talked about this, but I'm curious to obviously talk about this more publicly
Mm.
versus you and I just privately. But you've got all these other implications of space, right? You've got free power, which is great. You've kind of got free cooling. You just radiate the heat out into the space vacuum.
Mm.
You've got other implications like you have radiation in space, right? You've got those things kind of just blasting on the outskirts or the outer panels, etc., of everything you've got up there. You've also
Uh-huh.
got things like space debris
Mm.
and things that can at 5 kilometers of width, that's in the grand scheme of things not large in the grand scheme of space, However, it's still something that could get knocked around and bashed into by other things. How are you thinking about that? Would you have the ability to move this thing around? Obviously, you'd obviously need that to stay in the sunlight, through the orbit of, you'd be in the Earth's orbit, so you'd want to be, facing the sun at all times. So you'd need to have
Yeah.
propulsion. I'm sort of talking through the solution you've already solved for,
Yeah.
but how would you need to have some level of space weather on board that's aware of its environmental surrounds to move around, both autonomously and or manually from a base station.
Yeah, for sure. I mean, certainly for the foreseeable future, all of our satellites will have maneuverability, or the ability to maneuver out of the way of space debris and other things. Essentially, you want to avoid the congested parts of space if you're flying something very large like we are. And so, yeah, the first satellite we're actually flying very low, about 350 kilometers altitude. It's called VLEO, very low Earth orbit, and that's the problem there is you then have certain periods where you're behind Earth's shadow. But yeah, for the first few, it's fine for demonstrations and things. And it's what's called a self-cleaning orbit because everything naturally deorbits within a few months there because you have low levels of drag from the upper atmosphere, and so we need then to have propulsion to to maintain the altitude. For later versions, we'll be flying higher, around 1,200 kilometers, and that's the sort of lowest you can fly where you are 24/7 in the sun, in this dawn-dusk sun-synchronous orbit. Um, Nobody really wants to fly that high, and so it's very uncluttered orbit because because you're quite high into the Van Allen radiation belt at that point. I would say though that becomes less of a problem the larger the satellite gets, and the reason is if you want to put shielding around the satellite, the shielding is going to scale with the surface area of the satellite, whereas the compute scales with the volume, and so the larger the satellite, the lower the total proportion mass that goes into shielding.
Yeah,
So yeah,
that's
but yeah,
interesting. So when you go up there, are you having to on land, you have all these long time permits and challenges with, I need to, like, my power is in one county and I need to transmit it, somewhere else. I have losses. I have
yeah.
all this noise and time and effort. Like, how fast or slow, like, for someone, an ignorant non-space person like myself, and probably some others that might see this, you want to put something up in space. What do you have to do? Like, who
I
allows
mean,
you to stamp that thing and up you go?
once you've got the approvals, which you can get approvals way in advance, from launch to operation can be like a few months, and there's nothing really fundamentally slowing down. If once Starship is alive, the new launch vehicle from SpaceX, it's
Yeah,
expected to have way more capacity than Earth currently needs. So I don't expect there's going to be a huge constraint on launch at that point. So in theory, yeah, from chips coming out of factory to operating the data center could be 6 months. Um, so the real advantage is you can scale it almost indefinitely, and that's actually one of the main reasons we're doing what we're doing
yeah,
is the regulatory the regulatory constraints you have terrestrially. Like a new energy project of that size, of a sort of 50 to 100 megawatt energy project, you can be talking about 5 or 10 years lead time on permitting for that.
sure.
Whereas in space, we can launch almost as many of these things as we want. Space is huge, and so
It's in the title.
yeah, exactly. That's what it says on the tin.
Exactly. Yeah, the nutritional information is exactly accurate.
Yeah.
Yeah. So I was just thinking about, if you've got this propulsion system that you can kind of move things around, like, does the radiator, if you've got this heat coming off and you're basically, expelling this heat into the atmosphere or into the space
Mm.
vacuum, does it not create its own propulsion by virtue of kind of pushing that heat off, or does it naturally convect out? Like,
Very
how do
tiny,
you? Yeah,
extremely tiny. Yeah, the
insignificant.
yeah.
Okay. Um,
And
so that's
also
why
we're
you're
going to
doing this and
be
not me.
we're also the majority of the waste heat will go to like away from the sun, and we're getting there is some pressure from the force of the light from the sun hitting us, and also just protons and other things hitting us from the sun.
Yeah.
So if anything, we're going to be getting pushed in the direction that we're emitting infrared.
Okay, got it. And then from a like, what kind of you experience a similar lot, like the efficiency of those panels, and then the I guess the closeness of that system to the panels is probably unparalleled in most data centers that are out there today have solar on the grid rather than solar powering the data center because it's unfeasible to have that 24/7. It's
Yeah.
also that data center is probably not super close to where that solar array is on land. So you've
Yeah.
probably got a reduction of losses as a result of the proximity as
Yeah.
well. Are there anything special you're kind of doing there as it relates to that advantage? I mean, you could
Well,
keep all of the, you would own all of the power distribution, and keep it at a certain voltage and then you would have to then manage that downstream too. Yeah. Is there anything cool you're doing in that space?
well, actually, let's just touch on that comparison between terrestrial solar versus space solar as a means of powering data centers. Some people sometimes ask, okay, I've got a 10 square kilometer patch of desert. Is it more efficient for me to build a data center with solar panels on my 10 square kilometer patch of desert, or is what you're doing more efficient? And so I'll touch on why it's more efficient to do that in space, because that's a like kind of equal to equal comparison. So the three big costs you have terrestrially are, once you've got permitting to put a 10 square kilometer solar farm on a piece of desert, the cost of that land, the cost of permitted land, is actually probably the biggest cost of doing that terrestrially. So if you're starting from scratch and you want to do that terrestrially, you have to find a piece of permitted land and buy it. And that is extremely expensive. The price of that land basically goes up to match the discounted cash flow you get from the energy over the next 20 years. So it's basically, yeah, it's very expensive. Number two, particularly in North America. Number two is, if you are on Earth, you have a day-night cycle, and so you're going to need a lot of battery storage and a lot of backup power. And then the last point is you're going to need a whole bunch of solar cells. So in space, we don't need permitted land. So biggest cost is gone. We don't need batteries. We don't need backup power. So second biggest cost is gone. And we need 8 times less solar cells. So 1 square meter of solar panel in space produces 8 times the electricity of 1 square meter of solar panel terrestrially. So the only additional cost we have in space is the launch cost, and that is very rapidly trending towards zero, or trending towards
Yeah.
100 times cheaper than it currently is. But yeah, you're right. So because we don't have to run huge power cables, I'd say that's a fairly apples to apples comparison. That in the one where in the desert, you probably wouldn't need to run huge power cables either, although you would need to spend a huge amount of that power on cooling.
Yeah. Just
Yeah,
thinking about you said no batteries needed, and my mind kind of goes to Elon's cluster in Memphis, and so he's got
yeah,
100,000 GPUs out there. Lots of megawatts and even gigawatts of capacity over time. He's using his batteries to sort of smooth out the power fluctuations of these large training
yeah,
clusters. At 100,000 GPUs, the harmonics of that electrical system provide well, not provide, they produce instability by virtue of just full blast versus full off, very
yeah.
binary actions and reactions to sort of what's happening in there. How would you mitigate some of that at scale? In the small ones, probably less of a problem,
Yeah.
but at scale, then the power conditioning and fluctuations and stability would be challenging.
Yeah. No, yeah, certainly. I mean, you certainly need to condition the power coming. Raw power coming from solar panels is not in a form that's super usable, so you certainly need to condition it, and for that you need batteries and capacitors and step down in voltage and all these other things. Um, I would say though, our power source is extremely stable and constant. The power that we're going to be drawing from these solar panels is much more stable than any power source terrestrially. Even a gas turbine has less stable power than the power we're going to get from these solar panels. And certainly terrestrial solar is extremely unstable. Um, but yeah, as I understand, Elon is basically, I think he's bought every gas generator in North America to power that.
I think he's bought some from overseas too.
Yeah,
There
yeah,
was reports that he's bought, I don't know where from, but some power plant, gas turbine thing that is being shipped across, right? Like just couldn't get what he needed, so he just went, I'll just buy that one.
yeah, pretty much. Yeah.
You know, when you can, you can. That's cool. So you're obviously reliant pretty heavily on the Starlink. Sorry, pardon me, SpaceX, and getting their ships up and sort of piggybacking their launches. I think they've got a launch coming up here in August, sort of their 10th, flight to sort of, get up there. And the last one I think had a bit of a challenge. How are you expecting that one to go? Like is there anything, you're not putting anything in that particular, package or that load, for example. When would you be starting to utilize that? When would you see, Starcloud's infrastructure, starting to go up into space?
Well, we're launching stuff this year, next year, and the year after on Falcon 9.
Okay.
So regardless, we can be a profitable business just selling compute to other satellites at the Falcon 9 launch cost, and that's the business we're currently building. So, but when do I think the Starship will start putting stuff up? It looks like the first commercial payloads will go up, or the first non-Starlink payloads will go up in around 2028. So next year, I expect to see the first Starlink payloads, and they'll refine that whole mechanism through 2026 and 2027, and then likely seeing first commercial payloads from other companies going up 2028.
Yeah. So you're talking like satellite companies, you're talking like Project Kuiper from Amazon, you're talking about Starlink, there are others in addition to those two?
Do you mean for 2028 first commercial launches, or for?
Well, you're sort of building
Yeah.
those services for satellite providers
Oh,
outside of those.
who would we? Do you mean who?
Yeah, from a customer point of view, like utilizing those services. And I guess, if you think about what they would use it for, there's obviously a lot of telemetry going in and out of those systems, both up and down. But you're sort of talking about doing that, bringing that compute closer to that transmission, for
Yeah.
putting it up there in space and reducing the latency. Use cases like defense and remote deployments of compute needs, that type of stuff. Is that where you're expecting the workloads to be initially, or kind of long
Yes.
term?
Initially, certainly, yeah, DoD satellites would be one potential customer. Earth observation satellites, any satellites that produce a lot of data. I doubt it's going to be. I doubt Starlink or Kuiper would be our own customer initially, but yeah, it would be other satellites that are producing lots of data and don't have their own backhaul.
Yeah. And do you see that being like longer term and at that larger scale? Obviously a large 5 gigawatt, cluster up in space would be a fantastic training facility, right? Because you've got permanent cheap power or free power. You've got all that interconnected capacity that can basically work infinitely for free in space. Like training seems like a great workload for it. The latency kind of challenge is not sort of a problem, the bandwidth and or the latency, from a training point of view. But I would see a lot of inferencing being done that's not necessarily, not necessarily latency sensitive being done there. Is that sort of what you would expect as well?
Uh, Actually, I expect almost all inference in the end state will be being done in space as well. Actually, the space to data bottleneck is very quickly being solved by these optical relay networks, Starlink and Kuiper and others. So yeah, you actually have fairly huge capacity on each laser, up to 100 gigabit a second data rate on each laser, which is more than some full data centers have as their in and out pipe. So yeah, I expect in the end state, and the latency is like sub 50 milliseconds or sub 100 milliseconds to anywhere on Earth. So you could easily use it for
Inference.
running inference, any kind of inference really.
Would you then, I'm thinking about like a lot of these AI deployments today are, sovereign in nature and on soil in certain countries, from the UK, like the British government wants to do their own stuff in their own soil and other European countries the same. That's less important in the US and more important in Europe, seemingly. Then if it's up in space, that becomes kind of almost like a public cloud again. It's the everyone cloud. It's Starcloud. How do you see that kind of playing out? Is there advantages for that going up, or disadvantages from unable to kind of make that sovereign? Would you, if I think back
Yeah.
down on Earth, you think about companies that are kind of co-locating with other businesses and government organizations, and they'll cage off their compute, right? So you can't physically access it. But in that world, you've got people coming in and out. You've got, visitors driving past. You've got, all of these other challenges up in space, a little more difficult to get to. Operationally, we can talk about that too briefly, but, challenges with operating these things, fixing it, break fix, things. I've kind of just thrown a lot of stuff at you there, but, how would you think about, how would you think about that operational kind of impact, the sovereign nature that the companies or countries might be looking for, or is their solution it's on soil, it's literally on.
Yeah. I mean, so you have to sort of flag your satellite in a certain place. So if you're interacting with US ground stations, you need approval from the FCC, and then the US basically then the rules around your data protection and the data sovereignty aspect of that is basically then governed by the US. You can pick and choose. You can to a certain degree, you can pick and choose what regulatory environment you want to get your satellite approved in before launch. So, but yeah, and then you're basically beholden to the laws of that country. In terms of the maintenance and things like that, I think for the first few years at least will be similar to most satellites, like the Starlink satellites, in that we won't have access to them, and so we'll just require redundancy on critical systems and then over provisioning on the systems you expect to fail over time. So things like solar panels and radiators. Um, yeah, over time though, the whole space industry is moving towards robotic maintenance, and I expect that to be
Yeah.
similar for us too. And terrestrial data centers are moving towards robotic maintenance. And actually, with these massive mega clusters, there's a shift towards, it almost doesn't make sense to have somebody running around kilometers of racks pulling out individual H100s. And so now they basically, in some data centers, they just leave them in there when they break. And I think that would be a similar approach for us.
Yeah, so starting at 100% capacity, and things just eventually tombstone, to a certain point, and then you kind of clean them up when it gets to 7%, it's like, okay, we need to go and pick
Yeah,
some of this stuff up. Yeah, I noted when Meta did all their training for Llama 3, the main issues were reseating of GPUs, right? Like they become
yeah,
unsettled, and I think what the challenges they were finding was that it was all mostly air cooled at the time, and there's just a lot of vibrations, and if you put these things in immersion, that what we were finding at different companies I've worked with is the environmental stability actually improves because you've got there's more inertia in the environment, meaning a hot and a cold fluctuation actually evens out over time, which means
mm,
it's less traumatic for the electronics inside that environment. Therefore, they're less likely to die, and we saw that in data. And
interesting,
so,
super
yeah,
interesting. Yeah.
yeah. So, both that's just from a heat, but also vibration of the fans and all of the air rushing over it.
Mm,
But other issues that Meta sort of found were on the networking, like flapping network ports, and issues on that side.
yeah.
So
Networking's a nightmare. Yeah.
as you kind of get up, into higher speed and higher bandwidth areas, kind of different problems emerge, and things get even more sensitive. So, yeah, certainly the operational thing is, I think Submer's doing immersion cooling, and they're looking at, I think they've started developing robots to maintain these things, because the operational impact of immersion in traditional data centers is the operators don't really want to deal with it that much. They are very hesitant to. And so, okay, well, we'll just get the robots to do it. And, they work 24/7. So, you can
Super
see where
interesting.
that's going, and all of, Optimus, the stuff with,
Yeah,
from
what do you think there actually? I'm interested what your thoughts are. Do you think Optimus is going to be maintaining terrestrial data centers at any
I
point?
would love to see it. I mean, do I think it's going to
Yeah,
happen? I would like to say yes, because I'm an optimist in technology.
yeah,
There's just a lot of finicky small things that would
yeah,
need to change, and the challenge is, and you probably find this too, right, is that if you think about data centers and compute today, they are built around people. Like a rack
mm,
is not as tall as a 6 foot tall person that can't access the highest of RUs. Does
mm,
that make sense? Not really.
yeah,
If you take the humans away, makes no sense. And so
yeah, yeah,
we've seen things at different, conferences where they've got walls of compute, right? So it's like this is, you know,
mm.
easier to cool, maintain,
Network.
and network. And so when you don't have the constraints of a rack, you all of a sudden have the advantages of not having it, and
Yeah, yeah,
things become a little bit easier. You don't think about like 5 meter network cables between these nodes. All of a sudden, you don't need to wrap them and move them around, because a node has to be physically moved out and into the
mm,
front on rails. So, I like to think yes. However, the industry is so human centric. The physicality, the SKUs, even moving from air cooled to liquid cooling, whether that's direct to chip or immersion cooling, there's just a huge transition in applicability of those systems that don't necessarily play well with next gen solutions. So
Mm-hmm.
it's not, you can go and solve for one of them, but 99 other people have to go and solve their stuff to make your one work. So it's so I like to say yes. However, there's a lot of people that have to also say yes, stack hands and kind of move forward on a collaborative solution. And collaborative
Mm-hmm.
solutions take a lot of time. If you look at, a lot of these alternatives to NVIDIA, whether that's, NVLink alternatives or InfiniBand alternatives, it's years to do one small thing. So you think about the robotics of the finicky hand details of moving chips in and out and replacing DIMMs and power supplies. I think some of those things can get solved, but there'll be things that will take forever that are just locked into a human motion. Yeah. Thinking about power again, you've got this big old sun up there giving you free power. And I think the solution is, if you look at today's problems, there's a source problem, there's a distribution problem, there's a time problem, there's all these things, and they're full cost. And up there you go, I've got all those problems solved. If, for example, we're moving along the way with nuclear, and a lot of the hyperscalers today are going behind the meter, they're building their own turbines, like we talked about. They're getting hydrogen. So ECL is doing their own hydrogen-based, different, sources of hydrogen to sort of fuel their data centers. And nuclear is kind of, I won't say a hot topic, but it's certainly becoming less taboo. The red tape involved to both deploy and get, approval for these things is sort of going away. So in a world that approves, let's say, an aggressive approval, regulation to sort of get more of these out there globally, not just in the US, but Europe and Southeast Asia, does that negate the need to go to space?
Yeah. So the question is, if nuclear fusion or some other technology becomes very cheap, would we then need to build data centers in space? I'd say there's 2 points on that. Number one is um, the total energy cost we're targeting is considerably lower than the lowest forecast I've ever seen for nuclear fusion. So I think the lowest forecast I've ever seen for nuclear fusion was 20 cents per kilowatt hour from Helion Energy. We're targeting 0.2 cents per kilowatt hour, including the launch cost. So about 100 times cheaper. So
Yeah, wow.
even if fusion comes in at 2 cents per kilowatt hour, so that's number one. And number two is that there comes a point, and you can debate where that point is, but the rough back of the envelope math is it's somewhere between 10x total current energy usage and 100x current total energy usage, where it's not so much the carbon emissions or anything like that, but purely the waste heat from data centers and from energy production and usage on Earth drives the global temperature up so significantly that you start having huge problems, much greater warming effects and much greater problems than you would have with global warming. So you can debate about where that point happens, but at some point you just have to build data centers in space, or you have to build high energy use things in space. And it could be that you power them with nuclear fusion power plants if nuclear fusion comes to 0.2 cents per kilowatt hour. My suspicion is that solar panels are dirt cheap, and they are actually an extremely effective way of producing energy in space, more effective than nuclear fusion would be. But it could be, it could be that you would need to do it with nuclear fusion. Either way, the technology we're building is, how do we make chips run in a high radiation environment, and how do we dissipate heat in a vacuum? Those two pieces of IP will be valuable in either of those two scenarios.
Yeah.
In terms of where the power source comes from. So yeah, I'm very hopeful that fusion works. I'm a bullish on it, and I hope it works. But I don't think it solves the problem really.
Yeah. No, it's super interesting. I think it's, the sustainability angle, I think, is not really being talked about as much as it really should. If you just take one step back and you look at the hyperscalers kind of reporting, it's getting far worse before it's getting better. And I don't know if they're going to get better, because the need of demand to deploy all this AI at scale is meaning they're doing things that they perhaps don't necessarily, wouldn't want to do in the public market and talk about loudly, because those things aren't necessarily, they're doing more with less, but the more is not making the grand total go down to those, negative net negative targets that they've talked about by 2030 and 2040 and others. And so, that's, there's going to be a bit of a reckoning, public reckoning of those things happening in the next, months and years. That, the Googles and the Microsofts and the Amazons, they're not going to be able to talk about what, getting to these goals, because they're going to be shifting them dramatically. And to do that meaningfully means to do sort of work that you're doing, and change the whole dynamic of powering AI, cooling AI, all of the hydrogens gone in, off the Columbia River, to net new build power. It takes too long. So there's a lot of uh, headwind to sustainability that's sort of clear and present. And I think you're right. There's an inability for them to do anything other than reinvent a way to do it at scale. So yeah.
Yeah, very much so.
I know you got to bounce, mate. I really appreciate the time. Anything else you want to talk about, or you got to run?
Perfect. This is perfect. Awesome.
All right. Awesome. Thanks, Philip. Lovely talking to you, mate. All the best. Let's keep in touch. Love to do a round two of this, and let us know how the tests go. And yeah, we can keep talking about this cool stuff you're building with Starcloud. So thanks again for the time.
Thanks so much for having me on, Nick.